This is lecture 32. So in the last lecture we saw Noether normalization lemma. K field are finitely generated K algebra, or in other words finite type K algebra, then there exist algebraically independent Z1 through Zd inside R such that R is finite over the subalgebra K Z1 through Zd. So this is a polynomial ring or isomorphic to a polynomial ring, and R over this is finite. So we can go back to one of the earlier examples that we had this xy. Okay. So we can think of the subalgebra generated by x plus y. This was what was where we had mapped kt to this with t mapping to x plus y, and this is for example this is an example of Noether normalization. Okay. Okay, so now we will prove Noether normalization lemma in a little while, but before that we want to prove the Nullstellensatz. Okay. So first we'll start with a statement. Okay. We'll call it Nullstellensatz version 3 or version 4. We started with first version, which said something about V of I being empty. The second version was about maximal ideals. Third version was what we called classical Nullstellensatz, or Hilbert's Nullstellensatz was about the radical of the ideal, and now we are in version 4. Okay. Let K be a field and F an extension field of K that is finitely generated as a K algebra. Okay. Remember K to F is a ring homomorphism, and here we are saying it is finitely generated as an algebra. Okay. Then F is a finite extension field of K, that is it is a finite extension. Okay. So it is not at all clear what this has to do with Nullstellensatz and why it's even called a version of Nullstellensatz, so which we will prove now. Okay. So we will prove, so remember version 2 of Nullstellensatz, which we was that K algebraically closed, okay, M maximal ideal of R adjoint, K adjoint x1 through xn. Then there exists some A inside Kn such that M is x1 minus A1 through xn minus An. This is version 2. So now we will prove version 2 from version 4. Nullstellensatz version 2 from using Nullstellensatz version 4. Okay, so this is really, Nullstellensatz was stated as a theorem about zeros of polynomials. This doesn't look at all anything at all like that, but we would still call it a version of the Nullstellensatz. So we are in this setup. Okay. So let f be R mod m. So let R be the polynomial ring. So K is algebraically closed. R is K x1 through xn, okay, and m is a maximal ideal of R. Okay. Then R mod m is a field finitely generated as a K algebra. Because R is finitely generated as a K algebra, any quotient is also finitely generated as a K algebra, okay, which now implies this is the Nullstellensatz version 4. Nullstellensatz version 4 implies that R mod m is a finite extension of remember K is algebraically closed, yes, finite extension of K. Okay. So now K is algebraically closed, which now means that R mod m is actually isomorphic to K. Okay. So now let's try to look at this. So there is K here, then there is R here, then there is R mod m, which is also isomorphic to K. Okay. Now an element alpha inside K goes to the constant polynomial alpha and goes to alpha itself here, because this is just going modulo some maximal ideal. Okay. So alpha's residue class is just alpha itself. Okay. On the other hand, if you xi here will go to some alpha I for any I. Okay. So in other words, in this map, so this now implies that alpha I is the image of xi under this map. So under this map, then we see that xi minus alpha I. So alpha I, because it came from K, went to alpha I directly, and xi also went to alpha I. So this is inside M, because that's the kernel of this map. This is true for all I. So remember what, this is the image, this is the definition of image of xi in R mod m. It gives some element inside R mod m, call it alpha I. Okay, so this is inside here. So therefore, x1 minus alpha 1 through xn minus alpha n is equal to m, because this is a sub-ideal of this, but both are maximal. This is a maximal ideal for evaluation. This is given to a maximal ideal, so therefore there is equality here. So maximal ideal is of this form. Okay. So this is the proof of version 2 of the Nullstellensatz, assuming version 4. Okay. So now we will prove version 4 of Nullstellensatz, assuming Noether normalization, and then in the next lecture we will prove Noether normalization. It's a little technical argument playing with polynomials, but we will give a quick argument for some special case in this lecture itself. Okay, so this proves, so we now need to prove version 4 of Nullstellensatz assuming Noether normalization lemma. Okay, so version 4, proof of version 4. Of Nullstellensatz from Noether normalization lemma. Okay. So what is version 4 of the statement was a finite type, a field extension that is finite type is finite. Okay, this is what we have. And okay, so let f be a field extension of f of K, finite type K algebra. Okay. So then by Noether normalization, there exist Z1 through Zd inside f such that f is finite over K adjoint Z1 through Zd. Okay. But what can D be? Well, the claim is that D has to be 0. D must be equal to 0. Okay. Why? Okay. If D is positive, then Z1's inverse is inside F, but it is not inside K adjoint Z1 through Zd. That's because this is a polynomial ring. Okay? It does not contain inverses of the variables. So it won't be inside here, okay? But it is inside F because F is a field. I mean, Z1 is an element of F, so its inverse is inside. And moreover, Z1 is not integral over K, Z1 inverse is not integral over K Z1 through Zd. Okay. So it goes back to the argument as we did for integers and rationals. Okay. So suppose it is so. So okay. Suppose it is by way of contradiction. Suppose it is, then we would get something of the form 1 over Z1 to the n plus some a1 1 over Z1 to the n minus 1 and so on, an equals 0 with ai inside the subring. Okay. Clear denominators, we would get we would get 1 plus some a1 z1 plus right, okay, a2 z1 square up to some an z1 n equals 0. Okay. But think about it this way. Think about it. This is a polynomial. So now this happens inside the polynomial ring in K Z1 through Zd. Okay. That is not possible because all these terms have no constant term. Here there is a 1. Or said in other words, if these are algebraically independent, there cannot be such a relation. Okay. So this therefore D equals 0. Okay. And therefore it says that F is okay. So therefore F is a finite module, a finitely generated module over K, which is what we wanted to prove. That is, these are field extensions and that extension degree is finite. Okay. So therefore, we are now left to prove Noether normalization lemma. We would give the proof in the next lecture. But before we'll give the full proof whatever we stated in the next lecture. However, let's discuss a proof which will work in for infinite, much simpler proof which works in for infinite fields now, which can also be used, at least for fields that are sufficiently large enough, can also be used as an idea, as a trick to construct these things in a computer. Okay, so we'll do that in the next lecture, but let's just give a quick proof of this in the infinite field case now. Okay, so proof of the Noether normalization lemma. Okay, assuming K is infinite. Okay, so for example, any field of characteristic 0 or any algebraically closed field, all of them is fine. Okay. So write R as K adjoint some y1 through yn, because it is finitely generated, and map a polynomial ring to this surjectively. Okay. If this is injective, then there is nothing to prove, because then it's already a polynomial ring. Okay. If this map is injective, then R itself is a polynomial ring. Okay, and then we are done. Okay, because all that we wanted to prove was R is finite over a subalgebra which is a polynomial ring. So it's just even identity map. Okay. Otherwise, okay, some polynomial f, so there exists some non-zero polynomial f of y1 through yn in its kernel. Okay. So let n be the total degree, not individual variable wise degree, but the degree of f, the total degree of f. Okay. Now we do a change of coordinates. We do a change of coordinates as yi star is yi minus alpha I yn, and so this is for 1 less than or equal to I less than or equal to n minus 1, and alpha I to be determined. Okay. If you do this, then okay, so now we can rewrite f of y1 through yn as some f tilde of y1 star through yn minus 1 star yn. Okay. If you choose, in fact, for almost all choices of these alpha I, okay, f tilde, the new polynomial f1 star y1 star to yn minus 1 star yn, okay, is of the form sorry, I didn't, okay, so is of the form. So notice that the change of coordinates gives an automorphism of the polynomial ring, of this polynomial ring. Okay, so it is just that we are surjecting some other polynomial ring onto R. Okay, so it doesn't. Okay, so we can still study of the form. We can still study a non-zero element in the kernel. Yn to the n. So there will be some coefficient which depends on the alphas. So this is a non-zero coefficient from K. Okay. Then here onwards it would involve some coefficients from K adjoint the fewer variables. Sorry, yn minus 1 star, and then yn to the n minus 1 and so on, lower degree terms. Okay. In other words, in these new variables we get that, so this is a non-zero coefficient from K, so it's invertible. So without loss of generality we can relabel things and assume that f is monic, or f tilde is monic in Y, okay, with coefficients coming from the earlier variables. So therefore by transitivity of finite morphisms, therefore it's enough to show that the polynomial, the subalgebra generated by n minus 1 elements. Okay. So this one's image inside R. Okay. So this one's image inside R. So if we had yn also and then took its image, it would be all of R. But because of this, we don't need to worry about all of R. We can just remove that yn. So just look at the subalgebra that this one generates inside R. It's enough to show that this the image of this thing is satisfies the lemma, the theorem, the theorem, the Noether normalization lemma, and now we can proceed by induction. Okay, so then finish by induction. Okay, because it cannot come down all the way up. I mean, it might come down all the way up to 0, but at some point it has to stop. Okay. So this is the end of this the proof. This is a proof in the special case of where the field is infinite, and we would. So what does it actually tell us? I mean, concretely for computations. Okay. So suppose we had some k. So let's say k is infinite. So we are assuming k infinite. Okay. R we can think of as some k adjoint some y1 through yn modulo some ideal I, okay, finite type. So what it says is there exists general linear forms, okay, some d of them, which what is the value of d that we have not yet determined. It will take us a while for us to understand what the d is. Okay. So these forms will look like, well, maybe I should not call them, because they are images of in this thing general linear linear elements of R, okay, of the form. Okay. So these are the Z1 through Zd. Some summation alpha ij yj, j goes from 1 through n, I goes from 1 through d, and d will be determined later. I mean, that there is a d with this property is part of the lemma. How this current proof tells us that if you take some generic values for alpha alpha ij and construct these things, so let's call this thing zi, okay, So this we'll just take them as elements of R, or in other words, we'll construct them in the polynomial ring and then look at their residue classes in R. Then, sorry, there exists such that, okay, the subalgebra generated by is a polynomial ring, and R is finite over it. Finite as a morphism, so of rings. Okay, so this is the this is what thing. So we can actually do these things with linear combinations. This is what not every choice of alpha ij will work, but because k is infinite, we can there is enough room to choose them randomly, and that would work. That is what this may be useful in while trying to compute some things. Okay, and we'll see some examples a little later. Okay. So now, so in the next so this is the end of this lecture. In the next lecture, we will prove Noether normalization lemma in the generality. So that will finish the proof of Nullstellensatz also. Okay, so this is, and then we will study more about finite integral morphisms, integral extensions. And after we study that a little bit, then we can come back to computational aspects, or at least try to see some examples, pictures, etc.